Okay, so for this talk, M will be a smooth N manifold. And we want to study the following condition. So an immersion is totally non-parallel. If for all distinct pairs of points, distinct here, the tangent spaces each points contain no parallel lines. So we don't just want the tangent spaces to not be parallel, but actually there's no two lines of them that are parallel. So some simple examples. Parabola certainly has no pairs of parallel tangent lines. Take the same thing but complex. So map xy, y squared minus y squared 2xy, sort of complex z squared. And try to draw an example of S1 in R3. So certainly we can't have a circle in the plane with no parallel tangent lines. There will always be many. Here we can do something like this. You use your imagination. It's the shadow of this thing. This loop actually sits on the surface of a torus. It goes around in such a way that there's no two parallel tangent lines. Okay, so what are some very basic bounds we can get? We'd like to know, given a manifold, what is the minimum dimension? Such that there exists such an immersion. Okay, and from here we have Tn of R is R2, Tn of R2 is 4, and for S1 it's 3. And I don't know what it is for S2 or R3 or any other Euclidean space. So let's talk about some basic bounds that we can get. So first of all, just by the definition, we better have two n dimensions for two planes which span two n dimensions. If n is compact, we can get one more. This is simple Morse theory. You look at your immersion, and a generic height function will have at least two critical points. And there you'll have this 2n dimensional span and an orthogonal height vector. And genericity pretty easily gives an upper bound 4 times the dimension. We can dimension count and say that X and Y vary on an n-dimensional manifold, and so do the 2 tangent spaces. If you want to formalize this, you can do an easy multi-jet transversality argument to see that. Okay, so how about some better bounds? So we can construct some examples using a notion of symmetric bilinear maps, which are non-singular. So let me define this. Symmetric bilinear map is non-singular if the only way to get 0 is to plug in 0. These maps were studied a lot a few decades ago because they're also used to produce embeddings of real projective spaces. But in general, not a lot is known. I mean, they were studied a lot, but if you give me a value of n, say in the teens, I have no idea what the minimum dimension m is such that there exists such a map. So this also makes it hard to study totally non-parallel immersions, because we'll see that we can use these to construct them. So some examples. Real multiplication from R cross R to R is non-singular. Complex multiplication from R2 cross R2 to R2 is non-singular. These should look starting to look familiar here. And for a less trivial example, we could consider Rn as the coefficients of an n-1 degree polynomial and multiply these 2 polynomials together. That's going to be bilinear and symmetric in the coefficients, and it will give us, so this is degree n-1 polynomial, degree n-1 will get degree 2n-2 corresponds here. And the only way to get the 0 polynomial is to have that as one of the factors. So this is real polynomial.
The quaternions are not okay because it's symmetric.
Right. And yeah, there's something interesting here also, because the only time when it could be possible to have a totally non-parallel immersion of Rn into R2n is for 1, 2, 4, and 8. And I don't know if that happens for 4 and 8. We know R goes to R2 and R2 goes to R4, but we don't know if R4 actually goes to R8. If you like, because quaternions are not symmetric. You can do this for complex polynomial multiplication. So you'll get a little bit better bound when n is even.
So you mean if I take R4 to R8, which is quaternion squared, that
You will
map,
not get a totally non-parallel.
that map is not.
Yeah. Yep. Great. Okay, so why do we care about these? If you take a symmetric non-singular bilinear map B, and look at the graph of the quadratic part, so we'll define X, we'll define Rn to RQ. If this is symmetric non-singular bilinear, this implies that this map is totally non-parallel. Then a corollary, we can get examples in our 3n-1 when n is odd. 3n-2 for n even.
Sorry, what is the conclusion for that proposition?
Just that this is a symmetric non-singular bilinear map.
Okay.
Then this will be totally non-parallel. Okay, so yeah, as I said, these symmetric non-singular bilinear maps are related to embeddings of projective spaces, and you can get better obstructions for Rn in terms of some other problems people care about in algebraic topology. I'll mention immersions of projective spaces contribute to obstructions, and also what's known as the generalized vector field problem will also contribute to some obstructions. So for Rn, this problem is really sort of very intimately related to some of these classical problems in algebraic topology. Okay, but let's talk about some general obstructions for manifolds. So I'll use F2M to represent the configuration space of a manifold, pairs of unequal points. And let's take a map from M to RQ and define a map G on the product, which simply takes X and Y and adds their functional values. This is a Z2 equivariant map. It's easy to check with the actions which, switch to components here, but keep the component here the same. And if F is totally non-parallel, then this G will induce a map on the configuration space, ordered configuration space, which is an immersion. Maybe let me just define G to just become the configuration space. So F being totally non-parallel implies that G is an immersion. The differential at some point applied to a tangent vector can be decomposed as a tangent vector at X and tangent vector at Y, and this totally non-parallel condition says that they will not be parallel. So our obvious H principle question is the converse true? If we have an immersion of the unordered configuration space, can we then get a totally non-parallel immersion on the original manifold? In fact, I'm not exactly sure if it's true. I strongly believe this. In some metastable range that you can show this, and this will be about some ideas towards that and what I can show. So first of all, this also gives us a way to compute obstructions. And since we had no idea any any values of this possible dimension, I suspected that perhaps real projective spaces would be a good sort of test case, because real projective spaces are notoriously bad for embeddings and immersions. They take a lot of dimensions. So I spoke to Don Davis about this, who is an expert on immersions and embeddings of projective spaces. And he was able to show that this unordered configuration space of certain projective spaces, a non-immersion result for that. So showed that if you take a real projective space, which is a power of 2, the unordered configuration space does not immerse in 4 times that dimension minus 2. So that will give an obstruction to this totally non-parallel. So this must be greater than 4 times 2 to the m minus 1. And then what I was able to show is that for any manifold, you can put this in 4n minus 1. So we got together the exact value for real projective spaces, which are power of 2. Questions about this so far?
So what's the idea behind, or are you going to explain?
Yeah, this
Oh,
is
this-
the top.
explain us.
Yeah, okay, so yeah, the idea is, well, maybe first let me say this is sort of like a Whitney type result. We had genericity in 1 dimension above this. You know, Whitney says that generic map into 2 times dimension plus 1 is an embedding. Generic map into 1 less that is an immersion. And you can do this Whitney trick to show that there exists an embedding in 2 times the dimension. So this is similar where we have this genericity in 4n. We want to study some sort of local problem, which is generic here, and then manipulate that in some way to actually get one of these things in this dimension. And this manipulation is the removal of singularities technique of Eliashberg and Gromov. So I'm going to explain this technique for embeddings and then talk about how to use it for totally non-parallel immersions. Okay, so the situation now is we're looking just at embeddings into Euclidean space. And for F, I want to define, so I'll take this to be an embedding. Define this map G, which will take the difference this G is Z2 equivariant. Here, the action swaps here, but also is the antipodal map here. And since F is an embedding, this G has the property that the inverse image of 0 is exactly the diagonal of M. And Hefflinger's theorem is converse. So if M is closed, and we're in this metastable range, and if there exists this Z2 equivariant map this property, then there exists an embedding of M into RQ. Are we familiar with this theorem? So I'm going to give a fairly thorough argument using this removal of singularities technique. And here's the idea. We start with this map G, and we think of it as a list of Q real valued maps. So each of these is from M cross M to R. Collection is to RQ. And we have this property. And the strategy is we want to replace these components one by one with things of this form, of this difference fx minus fy. So the strategy is to replace one by one functions with this. And if we can successfully do that for all the components, then f is an embedding and we're done. Okay, so let's start with G1 and think about replacing this with the difference of a function like this, and think about what could go wrong during this process. So we'll replace G1, and what could go wrong is that we ruin this important property. This is what we have to preserve throughout the replacement of each component. So
Is the Z2 action not playing a big role?
it will, yeah.
Okay.
But here it's the negation on RQ.
Yeah.
It's not a constant action as it was for totally non-parallel.
So when will it not? Oh, okay, I get it. Okay, sorry. Maybe I'm asking why is it important to have that action? Or did that just show up?
It will definitely be used, but
Okay.
yeah, I was trying to think philosophically why it. Okay, I'll think about it, but
Okay, yeah.
we will use it. Okay, so we want to replace G1, and what could go wrong? We could ruin this important condition that we want to preserve through the replacement. But this is only an issue where these components actually hit zero. If they don't hit zero, I can do whatever I want with F1 and I can't ruin anything. For technical reasons, I want to not consider the diagonal. That, of course, will be in the whole pre-image, but I'm going to delete that and take the closure. So here's my picture. I have M cross M and the diagonal. I have this sigma. And I also want to consider the projection of the sigma down to this first factor M in the product. I'm going to talk about assumption on sigma. So here, pi is just the projection from sigma to m, and my assumption is that pi is injective. Okay, why is this important? So our end goal will be to consider this difference on all of m cross n. But we don't care about the value of the difference anywhere outside sigma. But we do have to be very careful on sigma that we keep this property. But f is only defined on n. So if we project down, we can use this image to define it on the image so that when you lift it back up, it will have this desired property. So this is why injectivity is important, to make sure that when you define it, you can lift back uniquely to ensure that this property still holds. So assuming this, let's define f or f1 on the image of sigma. And how should we define it? To take some input, lift back up here, and give the output that G1 gave. So I want to output G1 of xy, where y, well, technically where xy is exactly the inverse of pi. So here's xy. Sorry, here's x. Here's xy. And sigma is Z2 invariant because the G's are Z2 equivariant. This is one place that's important. So yx is also part of sigma. And y is down here. So let's check. Let's take an element of sigma. So maybe first of all, I should say, we have this f1 defined on a closed subset of m. And now we can extend it arbitrarily to the whole m because we don't care what it does outside of this. But if we do take a point, we do take a point of sigma and check what this value is. This is G1 xy, and because of this Z2 invariance, this one is G1 of yx, and G1 itself is Z2 equivariant, so this is 2 G1 xy. And this has to be non-zero, because we started with this list of things which don't map to 0, and G2 through GQ all map to 0 at this point. So G1 had to be the thing that saved us from 0. So this is not 0.
Sure, right. Doesn't that create any new problems nearby? Like if I had intersecting lines and I thought that they should be spread apart in the direction that ends, but just unlikely coincides with the tangent direction of one thing, then I move it along itself, then it just intersects in a different point.
Yeah, so there are some problems of this sort that we're gonna now try to address. Yeah, so yeah, so I think first of all, guaranteeing this assumption, but also, I mean, this will cause some issues near the diagonal, which you have to address very carefully. And that, it sounds like, is what you're asking.
More like nearby sigma, so that I just move it a little bit to the side rather than eliminate the preconditions.
Oh, then maybe I don't understand.
So if we have moved a little bit the image of X and Y, and we have to continuously extend it outside of sigma as well.
So I'm extending first before I even consider. So I'm defining it on this sigma, I'm defining on sigma in M and then extending it to all of M arbitrarily. So I don't have to extend it as sort of this difference of functions. I'm extending first and then taking the difference. And what the difference is outside of,
Okay.
yeah, that's,
Okay.
Are you assuming that sigma is somewhat transversely cut out, or but I mean, there should be some regularity of sigma.
yeah, so,
The injectivity is telling you that, right?
yeah, and I think, I mean, it should be a manifold.
Yeah.
For example. Yeah, these are some things that we have to be careful about.
Why does this F1 work? Like the difference isn't equal to G1, right?
That's why you're using the equivalence.
Yeah, you don't care. We don't want the difference to be equal to G1. We just forget about G1 and replace it with something else.
And what will you define F1 outside the sigma?
It doesn't matter.
It doesn't matter.
Yeah, because all we care about is preserving this property through the replacement.
You have to define something.
So you define F1 on this closed subset, and then you can extend it arbitrarily to the whole manifold.
Oh, it is pretty much zero only for
Yeah,
excluding the first one.
not G1, yeah.
Oh,
It's not G1, it doesn't have G1.
I missed that.
And you, like outside the sigma, you're preserving the property that the difference is G1.
No, I don't care what it is because these things don't map to zero, and all I care about is that nothing outside the diagonal maps to zero, but it already doesn't because these functions take care of that.
Okay.
But this procedure looks pretty good even if sigma is not a manifold. I mean, you're just projecting it down, whatever set it is, you extend it smooth.
Yeah, that's fair.
And then you take the difference as the new function.
Yeah, but
But it has to project, of course, down.
yeah, so yeah, the reason it's nice to consider that, yeah, so I want to think about this pi not just being injective, but actually an embedding. So then it will be convenient for sigma to be nice. So I want to think about this assumption and sort of when we can guarantee this. So if I want an embedding from sigma to M, generically, I might expect that I would need twice the dimension of sigma plus 1 to be the dimension of M. So, I mean, this is informal, but would like 2 times dimension of sigma plus 1 to be less than or equal to M, the dimension of M. So what's the dimension of sigma? Sigma is the pre-image of a point in a map into Q minus 1 dimensional space. So sigma has a dimension Q minus 1 in M cross M. So it has dimension 2n minus Q plus 1. So we'd like 2 times this plus 1 to be less than or equal to n. And if you work this out, this is exactly our metastable range assumption. So it seems plausible that this should work. But now what are the issues? So here's something which is not a true issue, but annoying. For genericity, it's nice to fix a space and consider generic functions to it. But here we're kind of fixing a projection and considering a generic space. The space will generically depend on G2 through GQ, but sort of formalizing this, I mean, we're looking at sort of some jet condition on sigma, but we want it to be generic for the G, and this is just annoying. But a bigger issue is that we can't really just perturb the G2 through GQ to ensure this genericity, because this condition, which we're trying so hard to preserve, is not open. So problem. You can't thoroughly perturb the G2. Okay, so what can we do? Well, if we look outside of a neighborhood of the diagonal, this actually is okay. We don't have to worry about anything because we can't ruin this. We can't ruin this property outside a neighborhood of the diagonal. But near the diagonal, we have to be very careful. And this sort of leads naturally into thinking about when you have a condition which is not just at a single point of a manifold, but a pair of points, such as embeddings or totally non-parallel maps. An important consideration is how this thing manifests locally. So if you think about this informally, you have a condition at pairs of points, you're bringing these points together, and intuitively, this should turn into a condition at a single point, but of higher order. For the embedding condition, you bring 2 points together. You know that their images are non-equal everywhere. This becomes the single point, single order immersion condition. So to study this problem near the diagonal, we want to understand how we can relate this to immersions. Okay, so the idea is now we have our picture. We have some neighborhood of the diagonal, which I'll call N. I'll choose N to be a Z2 invariant neighborhood, and also so that it looks like tangent bundle of N. Can do this somewhat explicitly. A point in this neighborhood is 2 nearby points in the manifold, and we'll map it to the midpoint together with the tangent vector here. So that ensures that because you do the midpoint, that ensures that the negation of the tangent vector will correspond to y. So here's xy, here's yx. This will correspond to this midpoint on the diagonal will be u. This will be a vector v minus v. So in this picture, here's u and here's v. We have this association where we map xy to u, v. And what happens to the Z2 when we switch y and x? We'll keep u, but negate in the fiber. So what happens to our map G near this diagonal? So we have a map G. Let me call H. Map G, which was defined on M cross M, just restricted here. Then H, considered as a map from TM to RQ, will be Z2 equivariant. And the condition we want to preserve turns into pre-image of 0 is the 0 section. Maps with these two conditions were studied by Eliashberg and Hirsch, and they're called Skew bundle maps. Notice that we have a map of a vector bundle to a vector bundle, but it's not necessarily a linear map. But it is Z2 equivariant, and it does sort of only map 0 to 0. It has this non-degeneracy. If it were linear, then this should be a injective map, a monomorphism, if you wanted to satisfy this property. So monomorphisms are examples, but in general, we don't require linearity. Nevertheless, Eliashberg and Hirsch showed that the space of skew bundle maps is homotopy equivalent to the space of monomorphisms. In a similar range here on the dimensions of the fibers. And then we have Smale-Hirsch, which tells us that this looks like an immersion. Now it's sort of all coming together. So the argument here is we start with our G, and we do this preliminary modification of G near the diagonal to make it look like it's an immersion, or the differential of an immersion, which can now be approximated by, so if I call my immersion that I get, the differential of this immersion d phi, this looks near the diagonal like this difference. I'm doing this preliminary modification of G to already make it look like this near the diagonal with this property preserved. And then outside of the diagonal, you can sort of go ahead with this replacement, perturbing sort of more freely. Still extremely technical and kind of a mess to make sure everything is glued properly. And also this thing I said, which was annoying, but not a true issue, which is, you know, genericity for sigma. Now it's more annoying because you don't just have the G2 through GQ outside the diagonal. You have that it's of a certain special form near the diagonal, which you have to also preserve when you do this perturbation. So it's just sort of a mess to control things both near and away from the diagonal and keep them glued and things like this. But in spirit, this is the argument.
One question. When we do Smale-Hirsch immersion, our perturbations are normally larger than the size of the neighborhood that we are dealing with. So will it be bothering to temporal sides?
I think I don't think you can guarantee that this is anywhere near the original G1. If that's.
No, I mean, we want to make it into immersion, preserving, well, meaning that it is immersion will automatically preserve that the image is only on the diagonal, but then we have to glue it with the G1 outside. And since we, like, the region where everything is fine, where it is immersion, is much smaller than the motion that we have done.
Right.
It seems that we could have some problems just kind of stepping outside of that region.
Yeah. Yeah, this is a good point. I want to say that because you have this, you basically have something with a boundary condition and then a map outside of that that you want to eventually hit. I mean, you don't care if it's G1, but consider the map, say, outside of a larger neighborhood and then interpolate between them, because these are, I think you should be able to do this without hitting 0.
Just because it's a general position. I mean, it's not like we. I mean, it's if it is an obscure thing, then I don't want to dig it.
Yeah, no, it's a good question, because this is one of the things when I did this for totally non-parallel that I had to be extremely careful about, and it was very annoying to be able to make sure that after I do this local thing that I could actually glue it back to something I originally had. And that was, yeah, but I think it should be a lot easier here by, I don't know, maybe just considering if you forget about avoiding 0 and sort of mod out by the Z2 action and think of this as a map from the unordered configuration space to some unit sphere, then I think you should just be able to sort of extend. I don't know. I don't think the extension problem should be a huge deal, but it's good to be careful about it.
Can you say one word about how to proceed for the other components? Because then the dimensions work differently, right? I mean,
So now you'll have to perturb. Now you have G1, or you have, sorry, F1. G3. Yeah, this is also.
No, but it's still Q minus
This
1.
is annoying. You just have to perturb them as functions on different spaces. You have to preserve this.
No, you can't perturb the first one.
You can, but you just have to.
You have to preserve that form.
You have to preserve it as a map here, and not as a just general map on M cross M. Yeah. There are a lot of annoyances. So maybe I'll just say a few words how this works for totally non-parallel. In particular, what's the local condition that we care about? For embeddings, it was important to understand immersions. Well, can we imagine this? We have 2 points converging, and we know that the images at these 2 points should have parallel or not parallel tangent vectors. So certainly as you move from one point to another, the tangent vector should be turning. This corresponds to some non-zero second derivative. But it's more than that, because if it's turning, but it's turning in a direction which is also tangent, then you're going to move it to something which was still tangent here. So you need the second derivative to be moving in directions which are not tangent directions. But let me try to formalize this. So given M, F, let me put some local coordinates near a point X so that we can carefully phrase this condition. I'll consider the differential at X, which I'm just going to think of as also going into RQ by associating the tangent space with RQ itself. And I will also have this second derivative I'll also think of landing in RQ itself. We'll call F semi-free if operator, let's say semi-free at X. If this is a non-singular bilinear map, well, of course it's bilinear and symmetric. We want this to be non-singular. And also that the image of this thing does not intersect the tangent space non-trivial. So these capture this idea that we're changing, but not changing in a direction which is actually tangent. You can combine these if you instead consider this projected to the normal bundle, then you can just say that it's non-singular as a map projected. So you could phrase this in terms of a second fundamental form.
I was about to ask.
Yeah.
And what is the phrasing in terms of the second fundamental form? Is it more elegant or?
I would just say it's non-singular as symmetric bilinear
Oh,
map
okay.
from this cross this into the normal
Into the
bundle.
normal bundle.
Yeah.
Okay, and then you get it.
Yeah.
All together.
Yep.
Okay.
So what about coordinates? Coordinate changes can change this image, but only with respect to something in the tangent space. So this condition is coordinate free.
How well with the second fundamental form formulation is even more clear, right?
Sorry?
I mean, if you formulate in terms of second fundamental form, then it's pretty
Then it's-
clear that
yeah.
that it's coordinate free, right?
Yeah. Semi-free because, well, we know free maps. Free is if the span of the first and second derivatives span the maximal possible number of spaces. They were also studied in this paper by Eliashberg and Gromov on removal of singularities, and apparently they show up in isometric immersions, but I don't know anything about that. Right, so generic map from M to R for n minus 1 is semi-free. And I should also say that semi-free implies locally totally non-parallel. Okay, so ideally the idea would be to repeat the embedding argument. So what do we do for embeddings? We first look near the diagonal, consider the immersion condition. We fix it there, and then we do this sort of general position argument outside the diagonal, glue everything together. In principle, outside the diagonal, everything is okay. It's a mess, but it works. But near the diagonal, so here we relied on these two big theorems of Affiliation and Smale-Hirsch, which I don't know if they hold for semi-free maps. So I don't have versions of these for semi-free maps in place of immersions. I don't have an H principle for these semi-free maps themselves.
Don't Eliashberg and Gromov prove some H principle for those?
They have it for free maps, but this condition is
So that doesn't
weird.
Okay.
This non-singularity, it's hard to understand. So So the problem with repeating the argument and getting this sort of generalization of Hefflinger's theorem is that I don't know how to properly control the diagonal.
And of course, the one of the three is not going to have any use for you because it requires a huge number of dimensions.
Yeah. Like n
The three
squared.
ones requires like n times n. I mean, almost n squared dimensions, so they can't use that.
But what I was able to do was, if I'm assured that I start with something which works near the diagonal, so if I know that a generic map is semi-free, then I can use this removal of singularities to fix it outside the diagonal and guarantee there. So this is the proof of this main theorem that this would be try to repeat exactly removal of singularities argument for embeddings. Outside the diagonal, this is okay, and near the diagonal, instead of using an H principle for semi-free maps, just use the genericity. Yeah.
So if you had the H principle, you could in principle go even.
You could go, yeah, you could do 7/2.
Yeah, but then you have a problem with your example, no? I mean, like because the theorem is sharp on the projective spaces, so.
Yeah, so there just wouldn't exist the necessary things for H principle.
But so doesn't that actually indicate that this 7 divided by 2n is maybe wrong? In this
No.
No?
This would say that if this holds and you have an immersion.
You start with the.
Yeah.
That's the data.
Yeah.
Okay, I understand.
Yeah.
So this could still be in principle possible, that
Yes.
that you can go below for n-1.
Yeah, definitely. So I think this should be true. Yeah, it was just these sort of missing components for semi-free maps. Actually, I recently heard Alvaro Del Pino had a student thinking about the H principle for semi-free maps. So I don't know the status of that, but maybe this is happening. Okay, that's it.
Thanks.
So where did this question first come up of? Not somewhere in geometry or somewhere in physics?
No, just my advisor in grad school, Sergei Tomashnikov, had studied a similar condition, except you also assume that the tangent spaces don't intersect. And he asked if there's an H principle for that. And that was very, very hard because that additional condition somehow is just a mess on jet spaces.
Yeah.
So I settled on this and yeah, but I don't know. I mean, there's this motivation, a lot of motivation coming from algebraic topology where the value for Rn is sort of related to these interesting problems, but otherwise it's just mysterious and fun to think about.
So this is all for the Euclidean space. So you mentioned S2 is not known. What is the best you know about S2 in terms of operations?
You can compute some Stiefel-Whitney classes because the unordered configuration space will have to immerse somewhere. I think the unordered configuration space looks like RP2. And I don't know, I could work it out. I mean, it's probably like 5 or 6 or something there, but I forget the exact obstruction you get.
But that's the obstruction. In terms of constructions, you don't have any.
No, just restricting.
Just the one that is like, the genericity thing.
Yeah, or you could take symmetric bilinear map from R3 and restrict it. But that might be worse in general, yeah. Or at least there.
Other questions? Well then, thanks.